All right. This is the office hour of tomorrow. This is the office hour of CS6505, and it is about minimum spanning tree. And let's start with problem 2 of the problem set 7. The problem 2 is about graph traversal. Giving a undirected connected graph G, and we need a linear time algorithm to traverse each edge once in each direction. That is to traverse each edge twice. And for a general problem like this, I will always approach the problems with a special case. Let's consider a tree. A tree is also undirected. It is a special. A tree is a special undirected connected graph. Let's draw this tree. Let's start with a simple tree made of only 4 tree nodes. And how can we traverse this tree with each edge being visited twice? And one simple idea is to create a path that is the outward boundary of this tree. You see this blue path. And this is true for any tree. Since there's no cycle in tree, we can always create this blue path. And for general undirected connected graph, there are more edges than this tree. For example, if we add an edge here, let's give a name to each of the nodes. V1, V2, V3, V4, and V5. Let's add an edge from V2 to V3. And the blue path does not work for this graph, but it does work for part of the graph. Let's try to modify this blue path to see how it goes. The green one follow this blue path. When we go from V1 to V2, now we are at V2. And we are noticing that there's a red edge, and this red edge does not belong to the original tree. For this red edge, we can go from V2 to V3, and then immediately go back from V3 to V2. And now we are on the blue path again, and we can follow the blue path. Let's suppose we add another edge from V4 to V5. And now we are follow the green path, we are at V4. We can treat V4 the same as V2. Go from V4 to V5 and then go back to from V5 to V4. And then we follow the blue path. Notice that the blue path, the green path satisfy the requirement that it traverses each edge once in each direction. Let's For the red edge, the rule is simple. Go back from the start point to the other node of the edge and then goes back from the starting point. But for a tree, how can we express the way we build this blue path? And it's very easy to solve this recursively. Suppose we starting from V1, and from V1 there's two edges. One from V1 to V2 and from V1 to V3. And if we pick the path from V1 to V2, now we add V2. For V2, if we only look at this one, we can, let's imagine the only graph is V2, and it is a trivial case. So it already satisfies the requirement of the path. Let's say we go back from V2 to V1, and then we go from V1 to V3. Now we're at V3. And for V3, we can draw the boundary of the subgraph. And if we complete the path for this subgraph, we start from V3 and then go all the way back to V3. And now we can go back from V3 to V1. So this gives me an idea of to call the routine recursively on each node that belongs to the tree. And with this idea, let's write down the algorithm. Call this algorithm make path. And start with U. U is any node pick. Oh, I forgot. So we need to first generate a tree from the graph. And notice it's actually a spanning tree. First, generate a spanning tree from G. And using DFS, the modified version of depth first search can generate spanning tree, and the time complexity is it's linear. Linear time. Let's denote the spanning tree as T. Now we start our make path routing as U. First, for any edge V that is adjacent to U, and we pass U from U, V belongs, let's start with the simpler case, does not belong to T. You see the red edge. And we go to start from U, go to V, and go back to U. And for V in adjacent to U, and the edge UV belongs to T. And remember that the recursive idea here, let's suppose from V1 to V3, and now we're at V3, we only need to consider the subgraph from V3, and the subgraph does not include the edge from V3 to V1 to see that V1 is the parent of V3 on the spanning tree. So we need to check an additional condition that V is not U dot parent in T. And for this, what can we do? We also start from U, go to V, and then we call image path V. Now, suppose we have complete all the edges that's adjacent to U. Now we need to go back, go from U to its parent, U dot parent. Okay, let's complete the algorithm. Let's start with our example. V4, V5. Let's try to apply the algorithm on this example. Suppose now we are at V1. Now we're at V1. And for each V and the spanning tree, suppose the spanning tree is this one. The red one is the spanning tree. Suppose from V1, let's consider V2 and V3 that is adjacent to V1. The edge V1, V2 is part of the spanning tree. So let's go back to this loop. So starting from U is V1, go to V, pass like this. So now let's call make path V, that is make path this. And we need to consider the does not belongs to. Let's consider V2, V3. This edge does not belong to the spanning tree, so it's in the first for loop. Start from V2 to V3 and go back from V3 to V2. So it's like this. Now we're at V2 and we're here. We need to go back to V2's parent, that is V1. And start from V1 again. Consider the edge V1, V3. It's part of the spanning tree, so it's in the second loop. So start from V1 to V3. Now we are at V3 and call the make pass algorithm on V3. So the make pass will create a path on this subgraph. For time's sake, let's say it completes this subgraph. Now we're at V3 again, so it's here. We need to go back to V3's parents, that is V1. So for the example, we have shown the algorithm works correctly. And let's analyze the time complexity of this algorithm. For the generation of spanning tree using DFS, it's linear time. And for these two for loops, we have shown that it traverses each edge exactly once. So for this part, it is all once. And yeah, that's it. So altogether, the whole algorithm is OV plus E. All right, let's see how to create new indirect. Okay, let's see what comes next. Oh, wait a minute. I need to check the second problem. The second problem is problem 6. And the problem 6 is covered in the last sessions of office hours. And I'm trying to follow this solution in last office hours and try to explain it in detail. Hope you could understand. So problem 3 it gives two constraints on the weights of edges. And the first constraint is suppose the weights are all integers ranging from 1 to V. all these problems. Let's try to write down the Kruskal algorithm. First, you need to make set for V. That is, this is initialization. And we sort edges by weight. Let's suppose the edges are E1, E2, and En, where n equals to E. Let's suppose the order E1, E2 to En is already sorted in non-decreasing order. Then we initialize the tree, the spanning tree, from empty. So for E in E1 to En, from E1 to En, let's consider the edges one by one, following the order long. So denote E to be U, B. And if E does not form a cycle in T, that is, in the textbook, it's find set operation of disjoint set, not equals to find set. Find set U will return the representative of the connected components where U belongs to. And find set V will return the representative of the connected components of which V belongs to. So this inequality will check whether the edge UV connect two connected components. So if UV forms a cycle, that means UV already belongs to the one connected component, and then this edge is not safe, so it should not belong to the spanning tree. So if it does not form a cycle, we include this. We include E to T and union to V. That means we merge two sets represent two connected components. Now they are connected by E, so they form a single connected component. So return T after the for loop is done. So let's analyze the complexity. For sorting edges, it takes, usually we use merge sort or quick sort. For it's n log n. Now the n is the cardinality of E for now it's the complexity for make set operation, find set operation, and union operation. You can refer to the chapter discussing disjoint sets. And for make set, it is O1. For the find set, since it is a find set is implemented using hash map, so the checking time is still O1. But for union set, it's alpha. V. And alpha V note that alpha V is very increases very. It's mentioned in the lecture that alpha V increases very slow. So for most cases, alpha V is smaller than 4 for most reasonable cases. So we can treat alpha V as constant time. Now, there's for the initialization, there's V make set. And for the looping, we check each edges. For each edges, there's find set. And in the worst case, there's find set and union. So, oh no. There's E find set. And the if condition is true when one edge is added to the spanning tree. So altogether, there's V minus 1 edges in a spanning tree. So there's a V minus 1 union. Let's simply put V here. If we consider alpha v as a constant type, then make set, find set, and union. The three operations all take O1. So V make set, E find set, and V union takes is approximately O B plus. And now we see the bottleneck is the sorting part. Also, the problem only changes the weight of graph. So, and only the sorting part is directly related to weights. So we need to figure out how to optimize sorting given the constraints. And if the value of the weights are restricted to 1 from 1 to V, and we can call using bucket sort. And let me briefly introduce the bucket sort. So suppose we have altogether there's 1, 2, and V. Altogether there are V buckets. We have an array of E edges. If we scan the E edges, or E edges, and put them in buckets. Let's suppose the edges with E 4, 2, 5. We scan the edges for V1. Let's put in this bucket. And for 3, let's put in this bucket. 3, 4, 5. And for 2, let's put it in this bucket. For 4, let's put in this bucket. And for 2, let's put in this bucket. For 5, let's put in this bucket. So what we get 5 lists. For 1, there's only 1. And for the 2, there's, I suppose this is V1, V2. This is E1, E2, E3, E4, E5, E6. And for the list of bucket 1, that's E1. For the list of bucket 2, there's 2 edges, E3 and E5. And for the list of E3, there's 1, E2, 4, E4, and for 5, E5. Notice that the value 1, 2, 3, 4, 5 gives a natural order of this one. So after we have scanning all the edges and put them in the bucket, this order is already sorted. And what is the time complexity of bucket sort? So it is linear. So it is linear for this one. And also we have the bucket. This is for initialization. This is for scan the array. So altogether, it's linear time. And this one, compared to the original OE log E, it's a huge, this one is a huge improvement over the merge sort. And let's consider the second case. Weights are all integers ranging from 1 to W or constant W. So for sorting, we'll get O E plus W. Oh, give me a second. If we follow the same method in the first case, we get the sorting in OE plus W. But what if W is huge? It is W bigger than E. So if W is very large, then we should not using bucket sort. And this will make the algorithm less efficient than that of the original merge sort or quick sort. But for huge W, what can we do about it? Let's consider a new algorithm called radical sort. Radical sort is basically multiple or rounds of bucket sort. Let me give you an example. Suppose the weight is represented by base 10. An example. That's an array 45, 75, 90, and 82. So for the first round, we always create 10 buckets. 10 buckets. Because it is base 10. We have 10 buckets, that is 0 to 9. And we only consider the last digit of each number. Let's suppose the edges are this. Edge weights equals to, it's this one. Let's assume it is only 0, 5, 5, 0, 2. How can we solve this using bucket sort? And the result of the bucket sort is this one. It's 90, 45, 75, 820. This is the result of the first round. And let's consider these second last digits. We only consider the second last digits and what the results of the bucket sort. And we should always put small number first. So 0 is the smallest. So 820. And what's next? Next is 4, 45. What's next? Next is 7. This is the first 7. So let's keep the original order if there's a tie. And what's next? 90. Let's consider the most significant digits. This is 8. There's no significant digits here, so let's make a 0 here. This is 1. Let's make a 0 here. Let's make a 0 here. If there's not enough digits, we just prepending 0. So for 0, 0 should come first. So it is 45, it is 75, it is 90, and here's 1, here's 802. This is sorted. Let's count the number of 3 bucket sorts. Why there's 3 bucket sorts? Because there's 3 is the number of digits. Number of digits in the largest number. So if oh no, why this is moving? Okay. Oh, this one is moving. Okay, let's put it here. So for base 10, if the range is 1 to W, we represent W in at most log 10 based W digits. So there's log 10 W rounds of bucket sort. Each bucket sort sort is all E. We need to scan the whole array and plus the number of buckets. So there's altogether 10 buckets. So for sorting, radix sort, the time complexity is 1 plus 10 times log 10 over W. So note that for merge sort, it's O E log 2 over E. So radix sort can be smaller than merge sort, even if W is bigger than E. Let's consider the case. Consider W equals to E equals to 20, or it's 33, and E plus 10 log 10 W is 33, 42. It's 42 times 3. It's and this one log 2 over E. It's 5. It's 32 times 5. It's 2 times 5. No, this one is bigger than this one. Even if W is 1000. So for the case when W is very large, we have an option of radix sort. So let's look at what's left for this problem. For problem 6, it's Prim's algorithm. So For Prim's algorithm, the time complexity depends on how you implement priority queue. If let's consider the first case, weights ranging from 1 to V. For this case, we use lists instead of priority queue. So let's suppose we have the lists. Let's IE. It's kind of like bucket sorts. So it's V lists and it's V buckets. This is V, this is 1, this is 2. And each one of them, each one is a list of edges. So let's consider the case 1. That's E1, E2, E3, E4. Let's start from the root. Let's start from the root and looping over all the edges. First, the edge is E1 and E2. Let's suppose E1 equals to E3 equals to 2. And E2 equals to E4 equals to 4. So when we consider E1 and E2, for E1, it is 2, so we put into bucket 2. And for E2, there's 4, we put into bucket 4. Now let's consider E3. It's 2, so let's append E3 after E1. And for E4, that's 4, let's append E4 here. So wait a minute. I need to check it's still recording.